Okay. So, good evening, everyone. Today is the fifth week of the live session of transport phenomena in biological systems. So, in today's class, we will see more about the momentum flux. In the last week, we have started doing the momentum flux itself, but today we'll be more into the momentum flux, right? That how, what is the behavior of momentum flux in pipe flow, in wet flow, in like that, in an annular flow, like that. Okay. So we'll be doing two derivations at first, and then we'll be moving to the question answer session. Okay. If you have any question, you definitely stop me and ask. And also, I will be solving some problems which will be helping you to solve the tomorrow's assignment. Okay. I think tomorrow is the target, right? Whatever it is. And this type of question may come in your question may come in your exam also if you are registered for exam, and also it will be coming for it will be helpful for your research perspective, and also your get, if you are giving get exam, these questions will be helpful in your get exam also. So let's get started. I am sharing my screen. I hope hopefully it will be visible. Yeah, right, my screen is visible. Okay. So first, whatever sir has solved in the class, that is the pipe flow, the flow, laminar flow in a cylindrical pipe, right? Laminar fluid in a cylindrical pipe. That derivation is very important, and we'll be getting some Hagen-Poiseuille equation, which is itself very important formula to calculate other things. Okay, so that derivation is important, so we'll be doing that. Another one is we'll be doing, which has not done in the class, which is the velocity profile of a falling film. Okay, so we'll be doing that too. This too we'll be doing. Okay, so the velocity profile in a pipe flow, right? So laminar flow in a circular pipe, we will be doing this. Okay, so this is your pipe. And this is your, suppose this is your axis. So we are thinking that this is the R direction and this is the Z direction. Okay, so theta is the rotational direction, this one. Okay, so we'll be taking the basic assumptions. So what will be those? First one, this is a Newtonian flow, Newtonian fluid. Second one is the steady state. Okay. Third one is the incompressible flow. Okay. Fourth one is the component of V, like So the fluid is flowing like this, right? So we are only interested in the velocity, like fluid has only one component, that is in the z direction, as you can see. We are not interested with Vr and V theta. So we will take as 0, 0 and Vz. Okay. So this is our velocity component. And we will also tell this gravitation is 0. So G is 0. Gz is 0. Okay. So now we can proceed to the equation. Okay. So what we can do? So now we will write the Navier-Stokes equations for. So we'll write the Navier-Stokes equation for cylindrical coordinate. Okay. First will be the arm momentum equation. So what it will come? So I am writing. So rho into del Vr del T plus Vr del Vr del R plus V theta by R plus del Vr del theta plus Vz del Vr del Z minus V theta square by R. Okay, this is the left hand side of the Navier-Stokes equation. Is equal to the pressure drop term minus del P del R, sorry, this is R, plus gravity term plus mu into del R into 1 by R del R into RVR, okay, minus, not minus, plus 1 by R square del square Vr square del theta square minus 1 by R square del V theta del Z plus del 2 Vr, sorry, del 2 Vr del Z2. Okay. Okay. So you can refer to the momentum balance equations from the BSL book itself. You don't need to write this. I am writing to show you why these terms are gone. So first term, as you can see here, so this is steady state. So this will be 0, right? Vr is 0. So this term is gone. V theta is also 0. This term is gone. This term is gone. 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 Gravity is not there. This term is gone. This term is gone. This term is gone. This term, everything is gone. What is left? Left is del P del R equals to 0, right? Next. Now, similarly, from the theta equation also same thing will be happening. I am not writing this again. I am writing the final equations for theta momentum. You can do it yourself that how these terms are gone. Here it will be similarly coming as del P del theta equals to 0. Okay. Next is the Z momentum. let's write the z momentum equation because it will be there. This term will be there. So what it is? Rho del Vz del T plus Vr del Vz del R plus V theta by R del Vz del theta plus Vz del Vz del Z. Okay. Equals to minus del P del Z plus rho Gz plus mu into 1 by R del R of R into del Vz del R plus 1 by R square del 2 Vz del theta 2 plus del 2 Vz del Z2. Okay, so now you can understand what terms are left. So this is 0, Vr is there, this is 0, the theta is there, it is 0. This is also 0 because it is a fully developed flow. Rho Gz is 0. This term is 0 because there is not changing with respect to theta, and this is also 0 because it is fully developed. So what are the terms left? So it is left is minus del P del Z plus mu by R into del R of R del Vz del R equals to 0. So this is the equation that is left, okay, because it is a z directional flow. Now what we can write is, now we can write it in the tau or form also, right? So this is the same thing. So it will be minus del P del Z plus 1 by R del R of R into tau RZ equals to 0, right? Because you know that we have learned in the last class that how the stress is defined. So tau RZ is nothing but your mu del Vz del R, right? If you compare with the equation, so mu del Vz del R is the tau RZ, right? So what is R? R is the direction of area where the change is happening, and Z is the direction of the flow, right? That we have discussed clearly in the last class. So now we can integrate it. So now we can integrate it. So what will be this coming? It is coming as del R of R tau RZ equals to del P del Z R. Okay, del P del Z into R. So now if we integrate it, what will come in? R tau RZ equals to del P del Z into R square by 2 plus C1, right? And what is tau rz? Tau rz will be del p del z r by 2 plus p1 by r. Okay. Now, if we apply the boundary conditions. So, what is the boundary condition? We can apply here. So, we can apply that at r equals to 0. That means at the middle length, at the center of the pipe, right? At the center of the pipe, the velocity we know that has to be highest, and the shear stress has to be lowest. So, what we can write? We can write that at r equals to 0, to 0, tau rz is finite, right? Tau rz is finite. So, therefore, C1 has to be 0. Okay. So, then what it is the coming? Then tau rz expression is coming as tau rz equals to del p del z into r by 2. Okay. Now, from here we can get the Vz. So, this del Vz del r equals to del p del z into r by 2, right? So, del Vz del r equals to r by 2 mu del p del z. So, Vz we are getting as r square by 4 mu del p by del z plus C2. So, what we can apply? We can apply it at r equals to r, Vz is 0. That we know that at the interface of the solid and liquid, the velocity would be minimum, right? So, what we can write here? So, if you write this, so you will get C2. So, what is 0 equals to r square by 4 mu del p del z plus C2. Therefore, C2 will be minus r square by 4 mu del p del z, right? So, your Vz will be now, Vz will be r square by 1 minute. So, Vz will be this, right? Yeah. It will be small r square by 4 mu del p del z minus capital R square by 4 mu del P del Z. Right? Now we can take common. What we can take common? If we want to take, we can take common minus del P del Z, and we will take common R square by 4 mu. Okay, so what will be? It will be, first one will be, so this term will come first, so it will be 1 minus small r by capital R whole square. Okay, so this will be your Vz. Okay, so now we can calculate the Vz max. Where will be the Vz max? Vz max, Vz will be Vz max at small r equals to 0, right? So if you put 0, what will be this? So Vz max will be minus del P del Z into R square by 4 mu. Okay, right? Now we'll calculate the volumetric flow rate. So you might see that my derivation is a little bit different from the what Sir has done in the class exactly, but it is the same thing. Okay, there is a little bit difference. Don't worry about that. This is the same thing, same way. Both way you can solve it. Okay, actually this is the same thing, but Sir has taken, I think, the pressure drop initially. So it was initially delta P by L. So there del P del Z is written as delta P by L. So he has taken that term. Yeah, he has taken that term, solved that portion of the pressure drop initially, but I have not solved it yet. You can think it as the pressure drop term. Okay, don't worry. So now what is the volumetric flow rate? The volumetric flow rate is Q, and it will be velocity integrated over the area, right? So it will be Vz, area is 2 pi r dr. So what will be the area? So this is your pipe flow, right? This is your pipe flow, right? So we are integrating is over the area this. So this distance is your r, and this distance is your dr. So we are integrating over this area. So it will be, for a circle, it will be 2 pi r dr. It will be integrated from 0 to capital R. So now 0 to r we know, Vz expression we know, that is minus del P del Z r square by 4 mu. Okay, 2 pi. We are taking the constants out and we will be multiplying r. It will be r minus r cube by r square into dr, right? Now you can say what will be coming. So this term is constant, you can take it out. Minus del P del Z. So r square pi by 2 mu. Then it will come as r square by 2 minus r to the power 4 by 4 r square, and it will be integrated from 0 to r. So now you put the values. So it will come as minus del P del Z r square pi by 2 mu. So it will be capital R square by 2 minus capital R square by 4, right? So what you can write Q as, Q is minus del P del Z R square pi by 2 mu into R square by 4. right? That is coming as pi r to the power 4 by 8 mu minus del p del z. Okay. And what will be the average velocity then? Average velocity, you can write it like Vz average. It will be like Q and its area. Area is pi r square. So now you can say this. So it will be r square by 8 mu minus del p del z. Okay. So now if you compare what is Vz ratio of average velocity and maximum velocity, you can compare. So what was the maximum velocity? If you see, so it is r square by 4 mu minus del p by del z, so it will be cancelled out. So r square by 4 mu by r square by, so it will be r square by 8 mu by r square by 4 mu. So it will be 4 by 8 into half, right? So this is the ratio. Okay. Now if you want to solve this, we can solve simply. So we know that the pressure, you can do it earlier also, no issue, but I am doing it here. So this is your z direction, right? This is your r direction. Pipe flow is happening from this side to this side, right? The length of the pipe is suppose L, and pressure drop at the initial stage is P1, and pressure at this outlet is P2. So P1 is greater than P2, that is why the flow is happening, right? So your minus delta P delta Z is P1 minus P2 by L. This is your delta P by L, right? So you can type like this. So now if you write the expression of your Q, so it was coming like pi r to the power 4, pi r to the power 4 by 8 mu into delta P by L. Okay. So if you write r equals to, also you can write as d by 2. D is the diameter, right? So what will be coming? It will be coming like pi d to the power 4 delta P by 2 to the power 4 means sorry to write. Let me guess. Just a minute, hold. Yes. Yes, we are for 16, and 16 into 8 is 128 mu L. Okay, this is the Q. Now if you want to solve for delta P, this is also a very important equation. You should remember it. Suppose I am now solving for So now if you want to solve for delta P, what will be coming? So delta P will be coming as 128 mu L Q by pi d square, pi d to the power 4, right? So it will be 128 mu L into Q by pi d to the power 4. Okay, so also we can write Q as 128 mu L. Q is nothing but your velocity, average velocity into average velocity V, suppose, into your area. So it is pi by 4 into d square, right? So pi d square by 4 pi d to the power 4, right? So now you can, if you can calculate, it will be coming as 32 mu L V average divided by d square. So if this equation is told this equation is told Hagen Poiseuille equations of pressure drop, and the previous one is the Hagen-Poiseuille equations of the flow rate, right? So from these two formula, we can calculate many things in a pipe flow, but this, you have to remember that this is only true for pipe flow. Okay. This is only true for laminar flow. Okay. Laminar flow in pipe. It is not also true for like turbulent flow. Okay. So this is the thing. You have to remember this. Okay. Next, we'll be doing the same thing, but for a falling film. So you can write velocity profile for a falling film. Okay. So suppose there is a film, this is the substrate, and there is a film. Okay. So I think I have done this in the last class. I think so. So that's why I'm writing the final equations. Then we'll be going back to the solving the equation. Okay. So here the equation is coming. Equation you have to deal with is mu d2y d by 2 equals to minus rho g. Here you will be coming as rho g by mu delta y minus y square by 2. Okay. So here the respective things you can calculate. Let's solve the equations. Then I'll come back. If some derivations is, if you think that is need to be solved, then the quick flow one, angular flow one, quick flow in a cylindrical system. If you think that that needs to be solved, we will do that. First, let's solve the equation or question answer. Okay. Let's go. So your first question is this. A boundary condition for velocity at the solid-liquid interface. Tell me. A boundary condition for velocity at the solid-liquid interface. So you know that at the solid-liquid interface, the boundary condition, the velocity, we apply no-slip boundary condition. In the last class, we have discussed it very clearly, right? No-slip boundary condition. It means U equals to 0 if it is stationary, if the plate is stationary, and U equals to V if the in case of wet flow. Okay. So what is your thought of it? So it is true that it is the velocity with which the solid surface is moving. This is option A. Next, which of the following statements are true in a well-developed laminar flow in a pipe without external forces acting? So pipe flow we have recently discussed, right? So we have told you that velocity will be, this is your Z, this is your R. The velocity profile would be maximum at the middle at r equals to 0, right? So this is your velocity profile, and this would be your stress profile, right? So the velocity of the fluid near the circumference of the pipe is minimum. That is true, right? Velocity is always maximum at the middle. The velocity of the fluid near the circumference is maximum. This is wrong. The velocity profile across the cross section of the pipe is parabolic. This is also true. Okay. Next question. A fluid will A fluid with a well-developed laminar flow is flowing in a cylindrical pipe of length x, such that the direction of flow is from x equals to 0 to x. The change in pressure P along the length is delta P, Px minus P naught. For a flow to occur, which of the following is true? So, what do you think? Which one is true? So, as you can see, pressure flow happens from high pressure from high pressure to low pressure. Always the fluid flows in this direction, right? So, if delta P is Px minus P naught, so P naught has to be less than Px, because this is the x equals to 0 position and this is the x equals to x position, right? So P0 P0 has to be high. Sorry, I have just mistaken. P0 has to be high. right? Because from here P equals to P0 and this is Px. The flow will happen like this from x equals to 0 to x position if only that P0 is high. Okay, so this is option B. And so delta minus delta P is positive. Okay, next. For the above flow, identify from below the equation for maximum velocity in its velocity profile. R is the radius of the pipe, mu is the viscosity of the. So we have just defined. So for this pipe flow, we have calculated what is the Umax. So as you can see here, it is the R square by 4 mu and pressure drop. Okay. So it will be R square by 4 mu into pressure drop. So it is option A. Minus delta P R square by 4 mu x. Okay. Next. The above pipe with same flow properties had to be used in an application that required the volumetric flow rate to be a specific 16-fold the current flow rate. If minus delta P is kept the same in the new operation, which of the following could satisfy the requirement? So we have to know the expression of Q. So Q, we know it is pi r to the power 4 by 8 mu. Okay. So Q is pi r to the power 4 by 8 mu into pressure drop. Okay, del P. So delta P is constant. Flow rate has to be 16-fold. Okay, so Q is proportional to r to the power 4. So initial is Q, this one is 16Q. And it has to be r to the power r1 to the power 4 by r2 to the power 4. So we have to calculate what is r2 here. Okay. So it will be 1 by 16 equals to r1 by r2 to the power 4. Then it will be 1 by 2 equals to r1 by r2. So then r2 will be 2r1, right? So it will be increase the radius of the pipe 2 times. Okay. Next. Capillary rise dynamics was used or studied for a mixture of ethanol and water. Okay. Capillary tubes of different diameters were used in the study. A high-speed camera was used to record the capillary rise. The data corresponding to the 80% ethanol water mixture rise is given below. The mixture had a surface tension of 24.7 surface tension, a viscosity. The capillary tube used had an inner radius of 0.3 millimeter and length 20 millimeter. The contact angle of the liquid mixture and the capillary was 60 degrees. Find the volumetric flow rate of the capillary rise. So capillary driving pressure, we know it as, so P capillary, we know it as 2 gamma cos theta by r, right? We can calculate it. So it is coming as 2 into gamma is 24.77 into 10 to the power minus 3. This is cos 60 degree divided by r is your 0.3 millimeter. That means 0.3 into 10 to the power minus 3. Okay, so what is the capillary coming? Hmm, 10 to the power minus 3 into cos 60, okay, divided by 0.3 into 10 to the power minus 3. So it is coming as 82.5667. Which is coming as 82.5667 Pascal. Okay. Now we have to calculate the volumetric flow rate. So volumetric flow rate, we know pi r to the power 4 by 8 mu into pressure drop. Pressure drop is the P capillary divided by the length L. Okay. So if you put these values, we'll get the Q. So we can do it in the next page. Also, you can do it here only. So pi r to the power 4 is 0.3 into 10 to the power minus 3 whole to the power 4 into 82.5667 divided by 8 mu L is 20 into 10 to the power minus 3. Let's calculate. Okay. So let's calculate. 0.3 into 10 to the power minus 3 to the power 4 into 3.14 into 82.5667, okay, divided by 8. Mu is your 1.14. So I have forgot to write mu. Write the mu value also. Okay. 1.140 into 10 to the power minus 3. Okay. Into 20 into 10 to the power minus 3, right? It is coming as Let's put the values again and do the calculation. I think I have done some mistake here. Uh, so your Q is coming as pi r to the power 4. It is 0.3 into 10 to the power minus 3 whole to the power 4 into P capillary is 82.5667, right? Then 8 mu was 1.14 into 10 to the power minus 3, 1.14 into 10 to the power minus 3 into 20 millimeters. So 20 into 10 to the power minus 3. Okay. So just simply calculate the terms. 3.14 into 0.3 to the power 4 into 82.5667 divided by 8 into 1.14 into 20. Okay, and the top one is coming as 10 to the power minus 12. The top one is 10 to the power minus 12 and this is 10 to the power minus 6. So it will be overall 10 to the power minus 6. So into it is coming as 1.1513 into 10 to the power minus 8 meter cube per second. Okay. So now it is said that it has to be in centimeter cube per second, right? Uh-huh. There is some calculation mistake or whatever, I don't know. You check it because this should come 10 to the power minus 6 actually. Okay, I think I have missed somewhere. So now you can write it as 1.151 centimeter cube per second, right? Which is option 4. Okay, you just check it please. Okay, where I did the calculation mistake. I couldn't find actually. Sorry for it. Anyway, just do. Now for the above flow, find the penetration velocity Vp. So Vp penetration velocity is the average flow rate by its area pi r square. So it has to be 1.1513 into 10 to the power minus 6 divided by pi into 0.3 into 10 to the power minus 3 whole square. So it is coming as 1.1513 divided by 3.14 into 0.3. It is coming as 4.07. Yes, it is coming as how come? There's something wrong in the equation or whatever it is. I don't know. So I think it should be 8. I think it should be 8, and if you want to match with the equation, I don't know what to do because it is not coming as simple as that. But I think this will be the closest answer as per there is some unit mismatch here. Okay, this is the actual one, and if you write this 8, it will be now coming as 4.073 4.0739 into 10 to the power minus 2 meter per second. So now you can write it as 4.073 meter per centimeter per second. Okay. So this is true. So that equation, that first question is some unique issues there. Okay. Next, in the tangential annular flow in a quad viscometer with a stationary inner cylinder and moving outer cylinder of length L, the cross section of which is shown below, identify the boundary condition that is best suited to get the velocity profile. Okay, so I think you can do this. So for this case, so there is an annular flow is happening. Okay, there is an annular flow is happening. Okay, and suppose there is this kind of situation. So there is a cylinder. Okay, and between this there is another cylinder, and this cylinder is stationary, the middle one is stationary, and the outer one is rotating. So what will happen? The rotated equals omega 0. So at r equals to kr, that means at the outer boundary of the inner cylinder, it is stationary, so v theta is 0. Okay, v theta is 0. And at r equals to r, capital R, that means outer radius, it is rotating with sigma r, omega r. So option C. Next. The torque needed to turn the outer cylinder in the above setup is given by 4 pi mu omega naught L r square into k square by 1 minus k square. So this derivation is completely done in the notes. Please go and look into it. Okay. Next. If there are n variables in a problem and these variables contain n primary dimensions, the equation relating all the variables will have, so back from Buckingham-Pi theorem, we know that n is the total variable. Okay. N is the fundamental variable. Okay. And n minus n will be the number of dimensionless groups. Okay, so option is A. Next. From the image of the cylindrical pipe shown below, identify the level profiles when fluid flows from x equals to 0 to x equals to L without external forces acting. So this AB is the, so this AB as we have drawn it, right? We have drawn it here. This here, right? So first one is the velocity profile. This is the velocity profile. This is the velocity profile and this is the stress profile. So AB is the velocity profile and CD is the shear stress profile. So it is option E. Next. For the above flow, identify from the above flow, identify from below the equation giving velocity profile across the cross section of the pipe r equals to radius of the pipe, mu is the viscosity of the pipe. Okay. So velocity profile expression we have derived. But it is asking for stress of what? So here gravity is constant. Gravity is included. Okay. So now you will get the velocity profile. So how can you just derive it? So here you can derive it. So here it is dx
এবং ধর্মনিরপেক্ষ নাগরিকদের কাছে আহ্বান জানাচ্ছি, আগামীকাল সন্ধ্যে ৬টার সময় উত্তরপাড়া বহুল সিনেমা হলের সামনে এক প্রতিবাদ সভা সংগঠিত হবে। এই প্রতিবাদ সভায় উপস্থিত থাকবেন সিপিআইএমের কেন্দ্রীয় কমিটির নেতৃত্ব ডক্টর মীনাক্ষী মুখোপাধ্যায় এবং সকলের কেন্দ্রীয় সদস্য। এই সমাবেশে আপনি একজন ধর্মনিরপেক্ষ সমাবেশকে সফল করে তুলুন এবং
So let's calculate from the above one. So we have the equation here. Initially we have done, right? So this is the Z momentum equation we are considering. So del P del Z is there, mu by R, del del R, R del Vz del R is there, and also the rho Gz will be there. You can see that this is the R, this is your X direction flow, and there is a gravity. Let's solve it. Is it a pipe flow? Yes, I think it is written pipe. Yes, yes. So this derivation we have done in the last class, if you remember. So from there, I am directly doing this. You can go back and check. From sir's note also you can check. So it can. So cos beta is coming that it is, suppose it is a inclined. Okay. We are considering that suppose it is an inclined field. So for the film also I have given it the equation. This equation here. So U is this, right? For the falling film also you can do, and you can change it for this. For the falling film, U is, for the falling film, U is rho G by mu into delta Y minus Y square by 2, right? And if we want to take du dy, so what will it be? Rho G by mu delta minus Y, right? So now put these values. So compared to this equation, we are finding this. This is the stress term dvx dx. So this is not the stress term though, but I think some missing is there. Question there is something wrong is there. So let it be. So we can write it like this, and it has to be, there will be a minus sign because it is going downwards. So it will be rho g cos beta I am taking because suppose it is inclined. So rho g cos beta by mu is has to be there, and there is a change in the direction, that is x. So you can, this is not a right question basically. But if you want to solve it like this, compare this with whatever is available. So give the options. Okay, this is not a right question. This is not a right way to do it. Let's go. Which of the following statements with respect to pressure is true in a well-developed laminar flow in a pipe without external forces acting? So pressure varies along the axial length of the pipe. Pressure varies along the circular cross-section of the pipe. Pressure does not vary along the circular cross-section of the pipe. Pressure varies with the angular position. So it is the first and third option you write from the discussion itself. It is true. Next. A pipe used in a bioprocess application had to be replaced with another pipe with half of the radius of the previous pipe. The flow properties had to remain the same to ensure smooth operation. Minus delta P is kept the same in the new operation. What is the change of the volumetric flow rate to the pipe? So we have done this. Q is proportional to R to the power 4, right? So if it is reduced, so it will be R by 2 to the power 4. So it has to be, Q2 has to be 1 by 16 of Q1. Okay, it is option B. Next, identify the equation from below that gives the shear stress profile across the cross section of the pipe. So for the cross section of the pipe, we have done this. What was the expression? Let's see. It is del P del Z R by 2. Okay, so it is just simply that. So del P del Z, the pressure drop, so you can write it also minus del P del Z, no issue in there. Del P del Z R by 2, right? So it is delta P by L delta P by 2L into R, right? So it is option A. Next. Capillary rise dynamics was studied for a mixture of glycerol and water. Capillary tubes of different diameters were used in the study. Okay, so this is the same equation, same type of problem, but the calculation has to be different. So we'll calculate for the P capillary. It is 2 gamma cos theta by R equal to, let's calculate first. Let's calculate first. So 2 into gamma is given as 65.3. I'm not writing the expression, you can do it yourself. Cos theta is cos 10 divided by R is 0.22. 0.22. So it's coming as 584.617. Okay, it is coming as 584.617 7 Pascal. Okay. Next will be calculating the volumetric flow rate. So it is pi r to the power 4 P capillary divided by 8 mu into L. So now put all the values and get the equation. Okay. So pi is 3.14 into r to the power 4, right? So 0.2 to the power 4 into 584.617 divided by 8 into mu is 20 into L 40. Okay. Into 10 to the power minus 3 to the power 4, that 10 to the minus 12 by 10 to the minus 6. That is 10 to the power 6. 10 to the power minus 6. It is coming as also unit mention. There is value is not exactly same. Why? Let me calculate again. Let me calculate again. Okay. So pi is 3.14 into r is 0.22 into 10 to the power minus 3 to the power 4 whole to the power 4. Okay. Into 584.617, right? Divided by 8 into 20 into 10 to the power minus 2. That means 20 into 10 to the power minus 3 means 0.02 into 40 millimeter means 0.04. Yes. Now it is coming. 6.719 into 10 to the power minus 10. Okay. 6.719 into 10 to the power minus 10 meter cube per second. So now you can think it of as this. So this is 0.672 in millimeter cube by second. So this is correct. This one is correct. Okay. Next. For the above one, calculate the Vp. So penetration velocity Vp is your Q by pi r square. Okay. So Q we know. It is just simply the 0.672 divided by pi into 0.22. It is coming as is coming as 4.421 into coming as 4.421 millimeter per second. So it is close to option 3. Okay, this is just like that. Next, using Buckingham Pi theorem, identify the number of dimensionless groups for pressure drop in a straight pipe. So for pressure drop, we have so total number of variable is 7. How I am calculating? So pressure drop is there, diameter is there, length of the pipe is there, viscosity of the pipe is there, density of the viscosity of the flow fluid is there, density of the fluid is there, and there is a roughness factor. And there is the velocity. So these are the 7 parameters. N is 3. We know that, right? N is 3. So dimensionless will be 4. 7 minus 3, 4. Next. So this dimensionless number or whatever I have taken, this will be different for all the situations. Okay, for pipe flow I have considered this, but for maybe for falling film or maybe for the annular case, we have to take the other parameters also, which are not important here. Okay. Next, for fully developed laminar flow of a Newtonian fluid down a vertical cylindrical pipe, which simplified differential equation describes the actual velocity profile VZR. So the cylindrical pipe and it is coming down vertically, right? So it will be mu by R ddr into R dv dz. So just how we have calculated the pipe flow. It has to be for the vertical one, and this P includes the pressure drop term and the gravity term. Okay, so this will be answer B. Next. In a vertical pipe with laminar Newtonian fluid flow, how are the maximum velocity and the average cross-sectional velocity? So for the pipe itself, we have seen that we have calculated this, that Vz average and Vz max is related to half, right? So for vertical pipe also, so for pipe flow this is true, so it is half. Next. If the radius R of a cylindrical pipe is increased by a factor of C while maintaining the same modified pressure drop, viscosity and pipe length, by what factor does it? So we have done it multiple times. Q is proportional to R to the power 4. So it will be 3 to the power 4, that is 81. So volumetric flow will be 81 times increased. What is the spatial distribution profile of shear stress across the radius of a pipe carrying fully developed laminar fluid flow? So it is parabolic. No, it is not parabolic. It will be constant throughout the entire cross section of the pipe. It is also not true. Linear with 0 at the center line and maximum magnitude at the wall. So I have shown you that. So it is like this. So it is like this. Option C. Next. According to the simplified Young-Laplace relation, what is the capillary pressure difference generated at the meniscus inside a capillary duct of radius r? So you know that it is the 2 gamma cos theta by r. You just remember this, don't need to go for the derivation, or if you want to go for the derivation, you can find it in anywhere, in any pressure book, in any transfer phenomena book. Okay. In microfluidic capillary flow, where capillary pressure is the sole driving force, what is the how does the penetration distance L of the fluid front scale with time t? So the length is proportional to root under t. Okay, it is option B. Next, liquid flow device with an inner stationary cylinder of radius kappa r and an outer rotating cylinder of radius r moving at angular velocity, what boundary condition sets the fluid velocity at r equals to kappa? So we have done this, it is d theta equals to 0. Next, during steady tangential annular flow in a of an incompressible Newtonian fluid, which component of the momentum balance equation simplifies to minus rho v theta square del p del r? So this is the R momentum equation, because R momentum component considers this centrifugal force term. Next, a biofluid with viscosity mu flows under laminar conditions through a microcapillary tube of radius r and length L. If the modified pressure drop is this, calculate the maximum axial velocity. So from the pi flow expression, we have calculated that Vz max is pressure drop into r squared by 4 mu. Okay. So pressure drop is 800, r square is 100 into 10 to the power minus 6 whole square divided by L is 0.02 into 4 into mu is 0.004. Okay. So what are we getting out of this? So we are getting 800 into 100 into 10 to the power minus 6 whole square divided by 0.02 into 4 into 0.004. That is coming as 0.025 meter per second. It is 0.025 meter per second. Okay. Just a minute. Let's cross check once. Mhm. Okay. Next, this is option A. Next. In modeling fluid movement in tissue regeneration scaffolds, why are whole tissues or organs frequently treated as porous media consisting of parallel capillary tubes? They consist of dispersed cells and interconnected voids through which nutrients and species travel. Adhesion forces between tissue fluids and cell membranes are identically zero. Pressure drops across tissue matrices are independent of matrix geometry. Fluid flow through living tissues is naturally turbulent at all scales. So this is the first question. So cells are dispersed and interconnected voids through which nutrients and species travel. So that is why capillary tubes are required. For fully developed laminar flow of a Newtonian fluid through a horizontal pipe of radius r, at what radial distance r from the center line does the local fluid velocity Vz equal to the average velocity? So Vz expression of Vz was r square by 4 mu 1 minus r square is this. Vz max is Vz max into this. Yes, so our Vz is, so we can write that our Vz is Vz max into 1 minus small r square by capital R square. So it is said that at what radial distance r from the center line the local fluid velocity is equal to the average velocity. The average velocity expression also we know, right? Average velocity expression is half Vz max. So if you equal these two, what will come? So it will be coming as 1 minus r square by excuse me, capital R square equals to half, right? So r square by capital R square will be sorry 1 minus half. So r will be capital R by root 2. So this is option C. This is a very interesting question. You need to solve this. Next. In a cylindrical pipe carrying steady laminar Newtonian flow, where within the pipe cross section does the maximum rate of viscous energy dissipation per unit volume occur. Viscous dissipation expression is like this. So we know that higher, so stress is viscous energy has to be higher at the pipe wall because at the middle the velocity is already high. So there is no point of viscous, there is no point of friction at the middle, right? In the channel. So the viscous energy has to be high at the pipe wall. So it is at R equals to R. From the logic also you can solve this. Two microcapillaries of equal length L are connected in parallel. Capillary 1 has radius R1 equals to R and capillary 2 has radius R2 equals to 2R. If a fixed total volumetric flow rate of a Newtonian fluid is passed through the parallel network, what friction of the total flow passes through the capillary 1? So we know that Q is proportional to R to the power 4. So for the first case, what fraction of the total flow rate passes through the capillary 1? Okay. So total Q total is Q1 plus Q2. Q1 is for capillary 1. It is nothing but the Q1. Second one is the 2 to the power 4. Second one Q2 is, so R2 is 2R. So that's why Q2 will be in proportional to 16, right? 16R to the power 4. It will be 16 Q1, right? It will be 17 total. So first one will be 1 by 17. Yes. Next. In a horizontal circular capillary tube of radius R, liquid penetration is driven solely by capillary pressure to gamma cos theta by R and opposed by viscous drag. Which differential equation governs the time evolution of the penetration front distance? So 2 gamma cos theta by R, this is the liquid penetration. Capillary pressure is opposed by the viscous drag. So viscous drag is 8 mu L by R square dl dt. Okay. It is from the Hagen-Poiseuille equation it is coming. So now if you solve this, it will come as L dl dt equals to gamma r cos theta by 4 mu, right? Gamma r cos theta by option B. Next. Integrating the capillary rate equation L dl dt equals to gamma r cos theta by 4 mu. From t equals to 0, L equals to 0 to time t yields the Washburn equation Lt is t to the power half. What is the explicit expression for the p factor c? So now we have to show the integration. So it will be L dl equals to gamma r cos theta by 4 mu into dt. If you integrate it, it will be coming as L square by 2 equals to gamma r cos theta by 4 mu into t Okay. So it will be coming as L equals to L square equals to gamma r cos theta by 2 mu into T. Then L will be just as it is. So L will be root under gamma r cos theta by 2 mu into T to the power half. It is coming. So C will be gamma r cos theta by 2 mu. It is option B. Root under. Next. For steady incompressible quick flow between two concentric cylinders, what is the velocity distribution? So this is already done. So you can just write it. This is option C. You can see the derivation in the class lecture. You will get this. Next. In steady quick flow between concentric cylinders with an inner stationary cylinder and outer rotating cylinder, what is the viscous torque per unit length? So torque is the viscous stress. That means shear stress into length, right? So T pi L will be the shear stress. Shear stress can be calculated from here. So if you know the V theta, so you will be able to calculate the shear stress into area, obviously. Shear stress into area into length. So it will be shear stress into area, that is the shear force. So it will be coming as, if do it yourself and you can match it with the equation, it will be coming as option B. Okay, just cross check if it is correct or not. A vertical open capillary tube of radius r is placed in a liquid bath. What is the equilibrium height that the liquid column reaches when capillary lift balances gravity? So it will be the radius 2 pi r into gamma surface tension force into the gravitational force rho g pi I r square into hq. So rho gh is the pressure into area, that is the force, and this is the interfacial tension. So HEQ will be coming as 2 gamma by rho g r. Okay. Option C. Next. A biofluid with dynamic viscosity flows under fully developed laminar conditions through a blood vessel segment of radius r. If the volumetric flow rate is this, calculate the modified pressure. So we know that Q equals to minus delta P by L into pi r to the power 4 by 8 mu, right? So minus delta P will be LQ by LQ8 mu by pi r to the power 4. So L is 50 into 10 to the power minus, or so you can write it like it is the 0.05. Q is 4 pi into 10 to the power minus 7 into 8 into mu is 0.003 divided by pi. So R is 0.002 to the power 4. Okay, now if we calculate what it will be coming, it will be coming as 0.05 into 4 into 8 into 0.003 into 10 to the power minus 7 divided by 0.002 to the power 4. So 8 into 0.003, 0. Into 0.05 into 4 pi into 10 to the power minus 7 divided by pi into, am I missing any calculation here? Let's do it again. It is 0.05 into 4 into 10 to the power minus 7 into 8 into 0.003. Okay, divided by pi is not there, so 0.002 to the power 4. Okay, I don't know why it is coming as 30. Okay, I don't know, maybe there is some calculation mistake. Hmm. Minus 7, 10 to the power minus 2, 10 to the power minus 9, 10 to the power minus 12 into 10 to the power minus 12. Okay. Divided by, so it is 4.8 into 10 to the power minus 10, suppose 4.8 into 10 to the power minus 10. I think they have done a mistake here. Whatever it is coming as 30 PA. You calculate, okay? If it is 300 PA, then it has to be option A. Okay, there's some mistake. Yes, it is. According to the Navier-Stokes equations, which physical mechanism is represented by the term this in the z component momentum balance? So as you can you know that this is the convective transport of the axial momentum. Okay, option C. Next. Derive the expression for the average velocity Vz in terms of maximum centerline velocity Vz max for fully developed laminar flow of a Newtonian fluid through a pipe by integrating the velocity profile. Okay, so we have these values. We are not doing this. So blood viscosity is blood flows through a microvessel of radius r and length L. If the centerline velocity is measured as Vz max, calculate the average velocity. So we know that Vz average is the half of Vz max. So it is coming as 12 by 2, this 6 millimeter per second, the first option. First question, the pressure drop across the vessel in Pascal. So the pressure drop we have calculated from the Vz max expression. Also we can do it. So from the Vz max expression, if you remember, it is delta P 4 mu L Vz max divided by R square. Go back to the derivation where I have calculated the Vz max and now calculate this. So 4 mu L. If give the terms, so everything is given. So I'm just directly calculating. Okay. So 4 into mu is viscosity is 3.5 into 10 to the power minus 3. Okay. Into L is 2 centimeter. That means 0.02 meter. And Vz max is 12 millimeter per second. That means 0.012 meter per second. Okay, is this divided by r square. R is 0.5 millimeter. So 0.5 into 10 to the power minus 3 whole square. It is coming as 13.44 Pascal. Okay. Next. Starting from a force balance on a cylindrical fluid element of length L and radius R, derive the relationship between wall shear stress and the pressure drop. So cylindrical fluid element, wall shear stress and pressure drop. Okay. So pressure drop is delta P into pi r square. This is the force and is equals to the shear force. That is 2 pi r L of the cylinder. Okay. So now tau W can be written as delta PR by 2L. Okay. Also R by 2 is, also D is 2R, right? So if you write it delta P D by 4L. Now you calculate. A heavy oil is pumped through A heavy oil is pumped through a horizontal pipe of diameter D and length L at a volumetric flow rate Q. Calculate the pressure drop required to sustain this flow. So just put the values. Calculate the pressure drop to sustain this flow, the resulting shear stress at the inner wall. Okay. So pressure drop we can calculate from the volumetric flow rate. We know that. So it is Q equals to pi r to the power 4 by 8 mu into delta P L. So delta P calculated from there. So it will be 8 mu L Q by pi r to the power 4. Okay. So put the values here. So what will be the values? So 8 into mu is viscosity is 0.25 into L is given as 15 meter into Q is given as 1.2 into 10 to the power minus 3, 1.2 into 10 to the power minus 3, okay, divided by pi into r to the power 4. R is 4, like r to the power 4, that means 4 by r is 2 centimeter. Then that means 0.02 to the power 4. So it is coming as 71656 71656.05 Pascal. 05 Pascal. Okay. And the tau, now just calculate this. Into D is 4 centimeter, right? 0.04 divided by 4L, right? 4 into 15. So it is 47.77 Pascal. So it is coming as 47.77 Pascal. Next, derive the volumetric flow rate formula for a fluid flowing vertically downward through a tube of radius r driven purely by gravity. Okay. So here what you have to do, I am just telling you what you need to do. You calculate yourself. So derive the volumetric flow rate for the, so Q we know for the pipe flow, but that is a horizontal pipe. But in case of here it is showing that it is the fluid is flowing vertically downward and it is completely due to the gravity and zero pressure drop. So in place of del P by L you have to put rho G. Okay. So if you substitute this, you will get this equation. Okay. So what is the volumetric flow rate? So Q is this. So pi r to the power 4 by 8 mu is as it is. In case of delta P by L, we are putting rho G. And now if you put the values, we will get your equation. The time required for 10 ml of glycerin to drain through the tube. So if you calculate this, you will get this. Let's do this. So 3.14 into R is 1.2 millimeter to the power 4. So it is 0.0012 to the power 4 into rho is 1260 into G is 9.81. Okay, divided by 8 into mu is 0.95. Okay, it is kind of 1.06 into 10 to the power minus 8. It is coming as 1.058 into 10 to the power minus 8 meter cube per second. Okay. So also we know that 1 cubic meter equals to 10 to the power 6 ml. So what we can write? We can write it as 0.01058 ml per second. Now, how much time is required to drain the 10 ml of glycerin? So 10 ml by this 1058 equals to, it will be coming as 9:45.18 seconds. Okay, so 9:45 seconds means almost 15 minutes, you can say. So it is almost 15.75 minutes. Okay, this is your answer. Next. So starting from the Washburn's penetration model, derive the expression for the instantaneous capillary penetration velocity. So I'm telling what you need to do. So this is the H square expression, right? So from there you need to calculate the H expression, HT. Okay, HT will be root under gamma RC cos theta by 2 mu into T root T. Okay, so from there Vp will be your dH dt. So you have to derive it, and from there you will be getting the calculate the liquid penetration distance. So from H, so if you put all the values in this equation, you will get And at t equals 0.5, we will get the first equation, and the instantaneous speed V cap of the liquid at t equals to 0.5 seconds is the same. So t will be same, and you have to get the expression for Vp from this derivation. You will get the answer for, put the values, and you will get the answer for Vp. Okay, I'm not doing it. You do it yourself. Next, all the five equations, all the five questions I will be telling you just like this, and you have to do it as assignment. Okay, just put the values, nothing else. Equate the upward capillary force with the gravitational weight of a liquid column to derive the formula for the equilibrium capillary rise HQ. Okay, so it is already told what to do. So earlier also we did, from there you will get this, you just equal this to 2 pi r gamma equals to rho g pi r square h. From there we'll get h eq is as this 2 gamma cos theta by rho g r. Now you put the values, you will get and in place of r you can write it as 4 gamma cos theta by rho g d. So if you put d equals to 0.4 and gamma is given, cos theta is 0, rho is given, g is given. So you will get the equilibrium height. Determine how much higher the water column would rise if the tube diameter were reduced to 0.1. So you can calculate, since height is inversely proportional. So h is, you can see, inversely proportional to d. So if d is reduced to 0.1, so accordingly, if d is reduced 4 times, so accordingly height will be increased 4 times. So you have to multiply the h eq, whatever value you will be getting from the first equation, with 4. Okay, so that is this equation. That is how you need to solve this. Very easy. For circular fluid flow between an inner rotating cylinder and a stationary outer cylinder, the torque formula per unit length is this. Derive this formula using tau or theta. So this is already done. I'm not going to do this. A concentric cylindrical viscometer has, so all the parameters are given. Okay. If the measured torque on the outer cylinder is also given, calculate the dynamic viscosity nu. So everything is given. You only need to put the value of, you need to get the value here. From here you need to get the solved mu. Solved mu from this equation. Thank you. Using the Hagen-Poiseuille volumetric flow rate equation, derive the expression for hydraulic pressure resistance RH delta P by Q as a function of fluid viscosity, tube length, and inner radius. Okay, so Hagen-Poiseuille equation, we know the formula, that is delta P, pi delta P r to the power 4 by 8 mu L, right? From the equation also, we had Hagen-Poiseuille equation we have solved. Right? We are solving the D form, this is the R form. Right? So RH is, so hydraulic RH is delta P by Q. So what is left? Left is 8 mu L, 8 mu L by pi r to the power 4. So compute the hydraulic resistance for water. So if you put all the values, 8 into mu for water is given, L is given, pi r to the power 4 is given. So you will get the hydraulic resistance for water. If the channel is redesigned with a radius of R2, keeping length L constant, calculate the new resistance and determine the pressure drop required to maintain the flow rate of 5. So RH is proportional to 1 by R to the power 4. Okay, is if radius is getting half, then the resistance would be the hydraulic resistance will be 16 times from what it was. Okay, and now you will get the new RH2, and from there you will be getting, you know, the Q, and you can calculate the delta P easily. Okay, it is very easy. Solve it yourself. I have told you how to solve it. Everything is given. Next, derive the flow rate per unit width for a liquid film of thickness delta flowing down a vertical wall under gravity. A thin, so this equation is, so the expression I have shown you initially, what was the expression for U for a vertical film, right? Like this. You remember the equation? Yeah, this one, right? This is the equation for U for a vertical film. So from here, if you integrate this vertical film, so if you integrate this U over its area, right? So the expression of U, you know that already given. So now for Q, you need to integrate it from 0 to delta. What is U I have calculated? Into dy, right? Q by W you have to calculate, because it is taking that flow rate per unit width. So you need to do this, and you will be getting the expression of Q like this. So it will be coming as, let me give the final expression for you. It will be coming as what is given, rho G delta Q by 3 mu. Exactly, it will come. And from here, you can calculate the surface velocity of the film. Okay, at y equals delta. So U expression you know, right? U expression you know. And from there, you can calculate the U expression you know. From there, you calculate for y equals, so U expression, let me write it for you again, rho G by mu, then delta y minus y square by 2. So it is said that at y equals to delta, so it will be delta square minus delta square by 2. That means then you will be rho G delta square by mu. So if you put the value, you will get the first solution, the surface velocity. You know rho, you know G, you know delta square, you know delta, you know mu. Then the total volumetric flow from, if you put the values here, all the values are known, and you will get the Q. Okay, or put all the values and get it solved, get it done. Okay, so this is it. So do these things by yourself. After putting the value, check the values if whether it is correct or not. If still you are struggling with the equations, tell me. I will be solving maybe in the next class, okay? Or you can definitely message. So I hope the today's class is clear. You have gone through lots of derivations and lots of problems which are partly done in the class, because everything can be done in the 2 hours class. So you go through the class notes carefully, because there also sir has done the derivations in a detailed manner. Okay, I have shown you the pi flow one because this is the most important one. And I hope from the equations I have solved, you will be able to solve this week's assignment, and further in other type of question also you will be able to solve. Okay. So we'll meet on next Tuesday, same time. Till then, goodbye.